Hello everyone. In this video we're going to learn about complex fractions. Really don't need to make the name scare you off with complex in it. All it means is a fraction that itself contains one or more other fractions in it. So the simplest kind you can get looks like this, where you have just one fraction divided by one other fraction. Now with this, we can of course just write it as a division. So a over b divided by c over d. Of course, we know that that means we're going to convert the division into multiplication and multiply by the reciprocal of c over d, which is d over c. So we get ad over bc. We notice a nice little relationship. It looks like when you divide a over b by c over d, you're going to get this outer product over this inner product. So this nice handy little shortcut we will use quite often, but it can only be used, keep this in mind, it can only be used when you have just one fraction divided by one fraction. And you can see that by the number of fraction bars, and it should just be one term and one term here. So we won't use it if there's more than one term either on the top or on the bottom of this main fraction. So let's go ahead and try the nice shortcut we just learned about with this complex fraction. We notice that we do only have one fraction on the top, one on the bottom, so we should be able to use it. So we'll go ahead and take the outer product. Now you do not need to multiply that out, just write it as a product, and then we're going to write that over this inner product, which is 15 times 16. The reason that you shouldn't multiply it out, even if it's a simple multiplication, is that when you write it just like this as a product, it'll be easier to do any cross-canceling at this stage. So notice that 8 goes into itself once, into 16 twice. 5 goes into 15 three times, and into 35 7 times. So we can see that on the top we're left with 1 times 7, which is 7, over 3 times 2, which is 6. And that's how you simplify a complex fraction like that. Now the exact same method can be used for simplifying complex fractions when you have variables in them, in other words complex rational expressions. So since we have only one fraction on the top, one on the bottom, we can use that method again. So we're going to go ahead and figure out the outer product divided by this inner product. So usually we write the term which has only the part that has only one term in it first, makes it easier. So we get x times x squared minus x. Here we're going to get x squared minus 1 times x squared. Again, it's easier to write the monomial first, so we'll have x squared times x squared minus 1. Of course, we know that x squared minus 1 times x squared is exactly the same as x squared times x squared minus 1. Think of this as a and this as b. So all you're doing is you're saying a times b is equal to b times a, which is called multiplicative commutativity, or the commutative property of multiplication. So anyway, at this point, we try to factor as much as possible and then cross-cancel as much as possible. So we notice that on the top, the x carries. We notice in this expression here that we can factor out an x. So be careful to make sure you write another x as a factor. So times x. Now we're going to be left with x minus 1. Now down below, the x squared will carry, and we notice that here we have a difference of squares. So of course we recall the f squared minus l squared formula, which is going to be the product of these two conjugates, right? So f plus l times f minus l. Here f is x, l is 1. So we end up with x plus 1 times x minus 1. And now we cross cancel as much as we can. First, we notice that x times x is x squared. So we have x squared on the top and x squared down here, which will of course cancel out, leave us 1 in all locations. And now we have, we really should just leave 1 on the top, because it's the entire x squared that's going to cancel this x squared. So we're not handling this one at a time. We're looking at them as one factor of x squared. All right, so just a little technical issue, but no big deal. All right, so here we can cancel out the x minus 1s. And that should be all the cross canceling that's possible, right? So now we write down what's left. Notice on the top, when those x minus 1s cross cancel, you're just left with 1s, right? So basically we have 1 times 1, which is 1. Down below we have 1 times x plus 1 times 1, which is just going to be x plus 1. And we are basically done simplifying that complex fraction. So now we'd like to take a look at complex fractions which have more than one term, either in the numerator or in the denominator, or both. The way we're going to handle these is going to include one of two methods. So we'll discuss two methods for handling such complex fractions. All right, so I refer to these as the classic method and the LCD method. Okay, so let's start with the classic method. Here we have, notice, more than one term. As soon as you get that plus between these two expressions, that means you have one term here, one term here, two terms, and we have two terms down here. So we cannot use our outer product over inner product trick anymore, because that only works when you have one fraction divided by one fraction. So here we're going to go ahead and treat the numerator and denominator as two separate problems initially. Just focus on 1 plus 1 over x. What would you do? That's easy, right? You can always go ahead and throw a 1 under the 1 and under this one to see it as a fraction. Now you find the least common denominator between 1 and x. Of course, that's going to be x. So on the top, so since we want to combine these two fractions, we need this common denominator, x. So this is a 1, so we're going to have to multiply it by x, which of course means we have to do the same on the top. Now this other denominator already has a denominator of x, so we don't need to do anything there. So the new numerators that we're going to combine, now that we have two like fractions, since both denominators are x, is going to be x plus 1. And down below, we do exactly a similar kind of thing. We notice we have a common denominator of x. We're going to need to multiply this denominator of 1 by x to make it like the common denominator. So we obviously immediately have to do the same on top. So the new numerators that we're going to combine are x and minus 1, right? So Now we notice we have reached a place where we have just one fraction over one fraction. So we can use our a over b over c over d trick. Remember? Outer product over inner product. So we get AD over BC. So we can use that now. So we're going to use it. So we get this product over this product. So we end up with x plus 1 times x. Remember, it's a little nicer looking if we write the monomial first. So I'll just write it as x times x plus 1. Same thing, of course. Down below, we get x times x minus 1, this inner product, remember? So x times x minus 1. Now we cross cancel. There's no factoring needed here. Those are simple expressions, no factoring possible. So all we can do is get rid of those, and that's it. You be very, very careful not to do any more illegal canceling, okay? You cannot cancel anymore because these are terms, they're not factors, and we only cross cancel factors, not terms, okay? All right, so that's the classic method. Now, this other method that we're going to use, I think you will like. Just like the table method, which was so efficient when it came to multiplying polynomials, the tabular method. This method we're going to discuss now for handling these is an extremely efficient method. So what we do, we call it the LCD method, because what we're going to do is we're going to view all of these as fractions, each of these terms, and we're going to find the LCD of all, notice 1, 2, 3, 4 terms. Now, those are simple fractions with a denominator of 1, but nevertheless, we can find an LCD. It's just going to be x. So what we do is we look at this entire complex fraction. We realize that whole part is the numerator of it, and this whole part is the denominator of that complex fraction. So we multiply. We know that we can multiply the numerator and denominator of a fraction by the same number or the same expression. So that's exactly what we're going to do. We're going to multiply the top and the bottom by that LCD. So remember, we find the LCD for all denominators involved, and that's just going to be x. So now we're going to multiply that LCD x on the top as well as the bottom. And notice we're going to distribute. So we need parentheses, or we can just go ahead and distribute. That means make sure that LCD gets multiplied by each term that you see, both on the top as well as the bottom, because we're going to distribute, right? So just that's the fastest approach. Just go ahead and make sure every term, because of distribution, gets multiplied by it. So now watch how simple this becomes. So we end up with x times 1, which is just x, plus, notice that here, when we have 1 over x times x, that x is on the top. So that cancels this x. So the two x's here cancel out. So we just end up with 1. So plus 1 over x times 1 again is x minus, notice those two x's also cancel out, leaving us just 1. So minus 1. Now you have to admit that's quite impressive, right? Look at all that we had to do here, and look how quickly we got to the answer there. Now, this is a particularly simple case. Sometimes, you know, as they get more interesting, the LCD method is going to be longer as well. This is not always going to happen, but you often are going to save a few steps compared to the classic method. So it's a very, very powerful and efficient method, but we love the classic method too because it helps us keep our fraction handling skills sharp. So both should be known. I expect you to know both of these methods because each has valuable techniques that you'll take out of the class with you. And of course, think about it. Doing them in both ways, if time permits, is a great way of checking anyway, isn't it? So if the answers are the same, it's very likely you've done it correctly. If there's any disagreement between the two answers, one or both are wrong. So then it makes you go back and check. This works really nicely with just plain numbers as well. Let's go ahead and try it here with this problem. Now remember, before we can use that trick, on the right side here with the LCD method, they need to be in improper fraction mode. But also in the classic method, we're still going to use the improper fraction mode first. So let's go with the classic method first. So 2.5, we know we need to multiply 2 times 2, which is 4, add to 1, which is 5, so we get 5 over 2. Let's see if we can do a better fraction line. So we get 5 over 2 minus, now here 3 times 3 is 9 plus 1 is 10, so minus 10 over 3. Down below we have 4 times 3 is 12 plus 1 is 13, so we get 13 over 3 minus 5 over 2. So now we're going to find the LCD on the top between these two fractions. That's just going to be 6, correct? So we get 6, and now we're going to go ahead and multiply 2 by 3 to make it 6. So of course we know we immediately have to do the same to the top of that fraction. And for this fraction, we're going to multiply the denominator by 2 to make it like the common denominator. So of course we do the same to the 10 on the top. So the new numerators that we're going to combine are 15 and 20. So we go 15 minus, let's go back to the other color. So we go 15 minus 20 over 6. Now down below, we're going to do a similar thing. The LCD is 6 again. Not always that way. This just happens to be in this particular example. Sometimes you have a different LCD, and that's fine because this is different from this method. In this method, we're going to get an LCD for all the fractions, but in this one, we're just working locally on the top and then locally on the bottom here. So to multiply 3 to get 6, we need a 2, so 3 times 2. Don't forget the top. And for 2 to get to 6, we need to multiply by 3. So we notice that the new numerator here is 26. And the new numerator here is 15. So now let's see. On the top we have negative 5 over 6, right? Over 26 minus 15, that should be 11, right? 11 over 6. Now we notice that we have one fraction over one fraction. We can use our outer over inner trick. So first of all, we'll deal with the sign. We have negative divided by positive, so the result is going to be negative. Now we don't need to worry about the sign anymore. We can just do the outer product, which is 5 times 6. And the inner product here, which is 6 times 11. Now we notice that we can cross cancel the 6's, and of course they leave just 1's. We don't need to write the 1's necessarily. All right, so we end up with negative 5/11. All right, so that's the classic approach, and it will definitely give us that result, right? So now let's do it using the LCD method. Remember, for the LCD method, let's make them all improper fractions first, like we did in the classic method. So we get, that's easy, we've already done it, but we'll do it again from scratch just to be sure we didn't make a mistake here. So 3 times 3 is 9 plus 1 is 10, so 10/3. And then 3 times 4 is 12 plus 1 is 13/3 minus 5/2. So now we're going to locate the LCD of all fractions that we see. There is 1, 2, 3, 4 fractions. The LCD for all of them, obviously that's just going to be 6. So the LCD is 6. So we're going to multiply that 6 on the top. And of course, I would have to write parentheses, except that I'm just going to go ahead and distribute. So I just make sure that the 6 gets multiplied by every term. That will save me one step anyway. And of course, I need to do the same on the bottom. So why is it we can do that? Why out of the blue can I do that? Because notice what we're multiplying by. We're multiplying this fraction, for instance. Well, the main fraction, we're multiplying by 6/6, like this, right? And then we're distributing like that, and then distributing like that. So why can we do that? Because we're multiplying by 1. 6/6 is what? Is 1. That's why we get to do this. All right, so let's cross cancel as much as we can. That should clear all the secondary fractions. We'll still be left with the main fraction, the mother fraction. So notice that 2 and 6 leave us 3 on the top. 3 and 6 leave us 2 on the top there. Here 3 and 6 leave us 2, and 2 and 6 leave us 3. So we end up with, all right, here we have to be very careful not to leave any terms behind or factors. 3 times 5, that's 15, minus 10 times 2, which is 20, over 2 times 13, which is 26, minus 5 times 3, which is 15. All right, so we end up with negative 5/11. And I think you'll agree this method was impressively short. Once again, extremely efficient, okay? Clears out the secondary fractions, leaving only the main fraction, which can easily be simplified. Make sure you can handle both methods before we proceed. All right, so let's go ahead and try this one. You should definitely be able to do this one by now. So go ahead and pause the video, work it out on your own, then come back. Remember, take enough time to work it out using both methods, and then come back and check both methods as we do it together. All right, so we noticed that in the classic method, we're just going to handle these two fractions on the top, just work them as if it's just one problem by itself. Notice you can throw 1 under that and under that if you like. So you can see the LCD on the top is x. That means this fraction is already good to go since the denominator is already x. This one we're going to have to multiply by x, right? Don't forget that means we have to do the same on the top. So what we're left with now is 2 minus 3x, right? Over x. Now, down below, the LCD of 5x and 1 is going to be 5x. This denominator, we don't have to do anything to make it like the common denominator, but this one we have to multiply by 5x. So that's what we'll do. Don't forget, you have to do the same to the numerator of that fraction. So now what we have left is 4 minus 10x, correct? All right, so now we're going to use, we recognize the fact that now we have just one fraction over one fraction, so we can do the outer over inner trick. So we can do that product divided by that product. So the outer product is going to be 2 minus 3x times 5x. Usually easier to write the monomial first. So 5x times 2 minus 3x over the inner product is going to be x times 4 minus 10x. All right, so I noticed right off the bat that we can cancel those x's, right? Now, here we do notice there's a common factor of 2, right? So the question is it worth my time to factor it out or not? Well, you should always consider factoring it out, but whether it's going to do much good or not is going to depend on whether there's going to be a common factor of 2 up here that maybe can cross cancel it to simplify things a bit. But we notice there is no such common factor of 2. The way 2 would have been reducible from this entire fraction is if it were in each of the terms, but it's not. So we can do a quick factoring just down here below, just so you can see. You can factor out a 2, and that would leave you 2 minus 5x. See, doesn't do much good. There's no canceling of these two or anything like that. So what we will do is, we will actually, now that we know it wouldn't have done any good, we'll actually leave it as is, right? We'll in fact go ahead and multiply the 5 into that group as well, just to make it look nicer and simpler. So we get 10 minus 15x over 4 minus 10x, and that's what we're going to leave as our final answer. Notice that we cannot cancel those or those because these are more than, we have more than one term. In other words, each of these is a term, and we never cross-cancel terms. Remember, we only cross-cancel factors. In other words, if I had 10 times negative 15x over 4 times negative 10x, that's what we mean when we say if we have factors. Then these are all factors, and we can cross-cancel as much as we want. We'd be able to cancel the 10s, we'd be able to cancel the x's, right? But there's a lot we would be able to do, but we don't have that scenario, and this is not what we have, so we don't. So we leave it just like that. All right, let's try the LCD method for this problem. So this time, remember, you're going to, let me go ahead and throw the ones down here. Remember, you're going to look for the LCD of 1, 2, 3, 4 fractions, right? Or 4 terms. So what is it? Well, you have x, 1, 1, and 5x. As you can guess, 5x is going to do it, right? That's going to be big enough to cover all fractions. So we're going to multiply the top fraction by 5x, and we're going to multiply the bottom fraction, I should say the top expression and also the bottom expression by 5x. So of course we're going to distribute now, so we're going to have, let's go back to blue. So we're going to have 5x times 2 over x minus 5x times 3 over 1. Downstairs, we're going to have 5x times 4 over 5x minus 5x times 2. Okay, so now we'll see how much canceling we can do. We notice here on the first term that we can cancel out the x's. In the next one, we don't need to cancel anything out. There's no common factors on top and bottom. So here we notice we can get rid of the 5 and the x, right? So the 5 cancels 5, x cancels x, and that's it. That's all the cancellation that's possible. So we're going to get 10, 5 times 2, minus 15x over all that's left here is 4 minus 10x. Look familiar? You have to admit, impressive method, isn't it? Very, very handy. But that does not mean this method is not extremely important and extremely beneficial to be very good with, because it has techniques that you need. So you need to know both methods. Don't just throw this into the trash can. It's needed. All right, so we see there's a common factor of 5 up here and one of 2 down here. So they won't cross cancel, so we won't factor them out. We'll just leave them as is. If we had a common factor in all 4 terms, that's a good sign, well, that we'll be able to do some reduction. So we'll be able to factor out the common factor on the top and then on the bottom, and then they will cancel and we get something simpler. For instance, if you had, let me go ahead and box this, we're finished. So just for argument's sake, if we had 10 minus 16x over 4 minus 10x, notice now 2 is a common factor in all 4 terms of this. So here it would not be a waste of time to take out the 2. That would leave us 5 minus 8x over, factor out the 2 downstairs, that leaves us 2 minus 5x. Then we cancel the 2's and we would be left with 5 minus 8x over 2 minus 5x. Remember, this is not part of the problem. This is one of the what if moments, right? So this kind of a situation, you would want to factor out the common factors, right? And notice the way you can tell that there should be some reduction is because you can see there's a common factor in all 4 terms. You don't cancel it out like this because that's not what we do with terms. You factor it out, then cancel it properly in this manner. Okay? Make sure you can handle those before we proceed. All right, so here's a nice new problem for you. Go ahead and definitely pause, try both methods, then come back to see if our answers agree. All right, welcome back. I'm sure you realize that on the top here, the LCD is XY. Remember, in the classic method, we just handled this subtraction and then handle this one separately as if they're different problems. Then we'll get the 2 involved using the shortcut that we have. So on the top there, the LCD is XY. So we're going to turn both of these denominators into xy. So to turn x into xy, we need to obviously multiply by what? By y, right? So that's what we'll do. And we realize we have to do that immediately on the top as well. To turn y into xy, we're going to multiply by what? By x, right? And immediately the same to the top, right? So now the new numerators that we obtain are y minus x, because y times 1 is y, 1 times x is x, and we have a subtraction, so minus. All right, down below, the LCD of these two fractions is x squared, y squared, right? So to turn x squared into x squared, y squared, we're going to need to multiply by y squared. And of course, we have to immediately do that on the top. And to turn y squared into x squared, y squared, we're going to have to multiply by x squared. And of course, immediately do the same on the top. So notice both denominators are now the common denominator. So we just combine the numerators, which are y squared minus x squared. All right, so we're already at one fraction divided by one fraction. So we can go ahead and do the outer product over the inner product. So we get x squared y squared times y minus x. That's this outer product, right? We wrote the monomial first. And this inner product, this times this, is going to be, so over xy. Remember, the rule says a over b over c over d equals ad, the outer product, over bc. Extremely handy to know. All right, so xy times y squared minus x squared. So now we factor as much as possible, and we notice not much to do up here, but down here we have a difference of squares. So we get x squared y squared times y minus x over xy times y plus x times y minus x. Remember that a difference of squares factors as a product of two conjugates, okay? So now we go ahead and cross cancel as much as we can. We know that x goes into itself once, it goes into x squared x times, right? Look, x times x is x squared, and you have x here. X goes into x squared how many times? X times. That's what we're talking about. All right, so notice that y goes into itself once, it goes into y squared y times. We can cancel out the y minus x here with the y minus x here. So you can see the final result, the simplified version of that original complex fraction, is going to be x y over y plus x. And there's the answer we obtained using the classic method, okay? All right, so let's go ahead and use the LCD method. Remember, for the LCD method, you have to find the LCD of all fractions or all terms involved. So we have x, y, x squared, and y squared. So what's the LCD? Remember, the procedure for LCD. Once everything is factored out, you multiply the highest powers of all factors to get the LCD, which is the LCM of all the denominators. So here we go, jumped off again for a minute. So here we have an LCD. So the highest power of x is x squared, the highest power of y is y squared. So the LCD is simply going to be x squared, y squared. So we'll go ahead and multiply the LCD on the top as well as on the bottom of this main fraction. So don't forget, there's going to be distribution involved. So we're going to distribute and distribute. So on the top, we end up with x squared y squared times 1 over x minus x squared y squared times 1 over y. Down below we have x squared y squared times 1 over x squared minus x squared y squared times 1 over y squared. So now we cross cancel as much as we can. So we notice that x here goes into x squared x times, into itself once, of course. Y here goes into itself once, into y squared y times. Down below, the x squared here cancels the x squared there, and the y squared here cancels the y squared there. So now we're left with, be careful not to leave anything behind, xy squared minus x squared y over y squared minus x squared. All right, as I told you, when they get more complex, the LCD method will also take a few steps to complete. The thing that is true is that overall the LCD method tends to be more efficient, and any kind of computation in it tends to be a little bit more tame. All right, so notice here on the top we have an GCF. What is the greatest common factor of these two terms? X, y, right? Let's factor it out. What does that leave us? That leaves us y minus x. You agree? See, multiply it out, see if you get this. See, x y squared minus x squared y. Okay, we're just factoring out a GCF on the top. Down below, we recognize a difference of squares, which means we'll use f squared minus l squared equals f plus l times f minus l. So we get what? We get y. Of course, f is y and l is x. So we get y plus x times y minus x. Now we cross cancel as much as we can. And there's not a whole lot. There's just the y minus x's, right? So we're left with xy over y plus x. If you like, you can even write it as x plus y. Sometimes we do that just because it looks kind of nice. And but they're exactly the same thing, y plus x and x plus y. This time it's because of additive commutativity, or the commutative property of addition. But notice we get the same answer. All right, so two different methods, both extremely important, both extremely useful, and really simple. Just have to be good, and you have to practice as much as you need till you're very comfortable with them. All right, so here's another one. Notice that we have negative exponents in this one, and we don't really simplify or do anything until we've turned those into positive exponents. So that's what we will do first. So we will rewrite 2x to the negative 1 as 2 over x. Of course, the rule we're using is x to the negative n equals 1 over x to the n. Let me leave some space here. So 2 over x minus 3 over y squared, using the same rule. Down below we have 3 over x squared minus 2 over y, right? Now, up on top here, the LCD is xy squared, so we're going to have xy squared as the common denominator. How do we turn x into xy squared? We multiply by y squared, right? And of course, we have to do the same on the top to make sure everything stays balanced. All right, now on the next term, the denominator is y squared. How do we turn it into xy squared? Of course, we're going to need to multiply it by x. We do the same on the top. Down below, we have x squared and y. So what's the LCD going to be? The LCD is going to be x squared y. Remember, we're not looking for the LCD of the entire complex fraction. Just one up here and the one down here. So notice that here, to get x squared to become x squared y, you're going to have to multiply by y, which is what we'll do. And remember to also do the same on the top. To make the y into x squared y squared, we're going to have to multiply it by x squared. And we'll do that here too. So now let's see what's left. So on the top here, we get 2y squared minus 3x, right? Down here, we get 3y minus 2x squared. Now we notice we have one fraction over one fraction. So we can do our outer product over inner product trick. So we get x squared y times 2y squared minus 3x. That's our outer product. Our inner product is going to be xy squared times 3y minus 2x squared. So now we go ahead and cross cancel if we can, and factor as well if we can. There's no factoring because the LC, like for example with these two, the GCF is 1, same here. So there's not much factoring possible. They're not like a difference of squares or any special form, sums of cubes, etc. So we go ahead and just cross cancel out here. So x goes into itself once into x squared x time, y goes into itself once into y squared y times down below. All right, so now we're ready to kind of write the final answer. So there's no more simplification possible, no factoring, so we can go ahead and distribute the x and the y to make it look nicer. So we get 2x y squared minus 3x squared over 3y squared minus 2x squared y. And that pretty much wraps it up for us on that one. All right, so let's go ahead and do the same thing, but with the LCD method this time. All right, so we are going to start out the exact same way. We're going to turn all those negative exponents into positive ones using this rule here. So we get 2 over x minus 3 over y squared over 3 over x squared minus 2 over y. So now this time we're going to look for the LCD of all 4 terms, right? So what is it? Well, let's see. X squared, y squared, y. So the highest power of x is x squared, the highest power of y is y squared. So the LCD, like the other one, is x squared, y squared. Now we go ahead and multiply x squared, y squared on the top and on the bottom, and then we distribute. So basically we're going to make sure each of these terms gets hit by the LCD, which is x squared, y squared. Now we cross cancel. So we know that x goes into itself once down there, and then x times on the top. Y squared cancel this y squared completely. Down below, this x squared cancels that x squared completely. Y goes into itself once into y squared y times. Now we carefully write down what's left. So we get 2x y squared minus 3x squared over 3y squared minus 2x squared y. So I think you can guess which method I will pick if I don't have to pick one. If one is not picked for me, I'm sorry, if one is not chosen for me, I will go with this method. You can see how quickly we got to that final answer. It's very efficient, okay? You must know this method well, but this is also extremely helpful. It really keeps your skills sharp with work when it comes to working with fractions. So both are really jewels of methods. They're very good. All right, now in this problem here, we may have wanted to factor out the x because we don't know any of this yet, right? So here we're seeing this for the first time if we've never done that, right? So we can see there's a common factor of x. We'll keep it in our mind and see if it's worth factoring out. We notice it is not a common factor down here. So factoring out up here, factoring it out up here would not really have done us a whole lot of good because we don't have it as a common factor here, so it wouldn't have canceled out and simplified. Notice the only way that would be useful is if you had an x in all 4 terms, and you don't. Notice the same goes for y. Yeah, there's a common factor of y down here, but there isn't one up here. And you can see what's causing the problem, this term. These 3 terms have y's in them, but this one doesn't. In order to be able to factor something out and then cancel out, it has to be a common factor in all the terms, okay? That's what you want to remember. All right, so that's pretty much it. Just one thing I wanted to give you a little warning about. When you get something like, when it comes to using that for outer product over near product shortcut, be very careful because something like that is very different from that. Okay, you're going, wait, they look pretty much the same. Notice it's going to matter where the main fraction line is. Okay, so since this is the main fraction line here, we're going to write a 1 under this 3, and then our outer product is going to be that, our inner product is going to be that. So we're going to get 1 over 6. Now, since in this one, since the main fraction line is here, you're going to want to throw the 1 under this 1 to make it a fraction. So we write that as 1 over 1. Now we can see that the outer product is going to be that and the inner product that. So we get 3 halves. So be very careful with applying the outer product over inner product trick if one of them is a whole number. You have to kind of determine where the main fraction line is and then throw a 1 under the whole number and then do the outer over inner trick. All right, and that should pretty much wrap it up for us for this video. So make sure you practice all of these and also more on the homework, and stay safe until we meet again in the next video.